Hello, everyone. Thanks for attending this seminar. I will try to give some introductory information about the most hot topics in deep learning models. Of course, there are a lot of different models and there are a lot of details. But due to the time constraints, we should be moving forward in a fast approach. Before we go into the topic of deep learning, let's see shortly what is machine learning, by the way. Well, most of the you know, but let's just review it. So it's just the study of algorithms that learn from examples and the experience instead of relying on hard-coded rules. So there is a training stage, and with the aid of some algorithms, the software, the system learns, and it can predict or relate, associate with the new data. So that's the basic of the machine learning. And when we come to the deep learning, well, that's a subfield of machine learning or AI. Why do we call it deep? Because there are a lot of deep operations, mathematical advanced operations, and in most of the cases, there are a lot of layers, successive layers, and there's information going on within these layers. And in the end, the system just drives the meaningful representation of the data. And this is a good approach. So the biggest domain is the artificial intelligence, and machine learning is a subset of this domain, and deep learning is another subset of this domain, which has become the hottest topic in the last decade and today, the deep learning. As I told you, in machine learning, so if it's supervised learning, for instance, you have a labeled data, so that you have an objective attribute, and you try to classify, or in terms of regression, you try to numerically predict it. And what is the crucial thing in machine learning and in both deep learning and any type of learning is there is a real learned model. So you just divide your data into two, training data and the test data or relation data. And with your training data and within the algorithm or the parameters of your algorithm, whether it's a neural network or decision tree or some other machine learning algorithm, it drives eventually at the end of the training stage the model. And after you finish your training stage, you use this model, and then you try to predict or accurately classify the new coming data, which is the test or validation data. So this is the basic idea in the case of supervised learning, because there are different types of learning in machine learning. But the crucial thing is, whenever you think about the machine learning, there is a training stage, even it's unsupervised or reinforcement learning, whatever. So if it's classification, think of it as a representative function. In some of the cases, this could be a real function, but in most of the cases, like neural networks, decision trees, and so on, it is a model. And in the case of neural networks, it is a black box model, because the only thing is trying to adapt to a very difficult nonlinear problem with some aid of the parameters, weights, and according to those weights, it tries to learn. And as I told you, in the training, you train your model to establish a final saturated structure, and then you try to guess or predict the data that has never been seen before. So this is the crucial thing. If you are dealing with unsupervised learning, the supervised is the previous one, but in unsupervised learning, it could be either clustering, but not only clustering, it could be something else. It could also be, like we will discuss today, some autoencoders for image reconstruction, reconstructing the data, reorganizing the data. It's also another type of unsupervised learning, or clustering algorithms. So again, from the data, we try to get the new features, or from the data, we try to cluster them into meaningful different groups, set of groups. So there is no target objective attribute, which we call class attribute or regression attribute, but we try to separate the data. There is also another type of learning which is very different, reinforcement learning, which is mostly used in different types of computer games or strategy games or traffic signaling or server load balancing. So it's based on some temporal distance or some other policy learning algorithms. So the algorithm is based on the agents with the rewards or some discounts, and it iteratively, like an optimization problem, within some iterations, it tries to get the optimal solution according to the rewards or Q tables, whatever you use as your reinforcement strategy. So in traditional machine learning, now we are coming to the requirement of the effect of the deep learning. So think of a picture, either a grayscale or like in this one, a nice cat picture with RGB, a color picture. So if you try to classify this as a cat, and if you try to use some classical algorithms like as a single hidden layer, multi-layer perceptron, or a decision tree, or another algorithm, radial basis function whatsoever, you have to handcraft the features. What I mean is that, for instance, if this is a 100 to 100 pixels and an RGB, this means that this will be eventually 30,000 different attributes, and it won't be very effective to use all these attributes. So either you use all these attributes and you get with a low accuracy, with high error, or you try to reduce these attributes with some very well, I should say primitive statistical methods or some other handcrafted methods. So it is not very effective. However, this brings the importance and the effect of the deep learning, because in deep learning, for instance, which we will see shortly after, the convolutional neural networks, the system learns from the features by itself, and it progresses, it moves on, and it advances, and it comes to the highest level of features, so and it classifies as a cat. So it doesn't use all of these original pixel attributes in the final learning model. It derives some different patterns, meaningful patterns, which these meaningful patterns, I should underline, is not meaningful to the human eye, but to the computer vision. Another important aspect is when we think of classical data mining or traditional machine learning, in the right-hand side, it could be either tabular data or time series data. It uses some traditional computational statistics or some simple machine learning algorithms, which is only, it could be used effectively by CPU. But when we think of much bigger data with much complex architectures, we come to the deep learning with the aid of GPU or TPU also, and very complex problems with much higher amount of data and requiring much computational complexity on the left-hand side. And keep in mind that there is also another issue which is true for all machine learning aspects, including the deep learning, is the no free lunch theorem. So no single classifier or no single algorithm or no single deep learning model works best for all the possible problems. So we should make assumptions. So even for deep learning, your convolutional model could be very accurately classifying for a problem, but it could not be working as that for another different type of problem. And another important issue in deep learning and machine learning is the generalization, which gives the power of these machine learning algorithms as well as deep learning models and algorithms. The generalization is just like human beings. For instance, these are different categories like dogs or apples and tomatoes, and you train with these different apple images. So the thing is, if it really learns, then it is a good generalization, your model, your algorithm. So if a new apple comes with a very different image, it again correctly classifies as an apple. And also keep in mind that if it is a really good generalization power, even trained with these green apples, it could also see this as an apple. Or if this apple has a bad shape, some part may be decayed, even with those decay marks on it, it could also generate it again accurately as apple. Then it is a good generalization power. And this generalization is mathematically based on basically 3 parameters, but 2 of them are very crucial. They are bias and variance, and they are somehow in a competitive way. So they affect the 2 most important aspects in machine learning as well as deep learning. One of them is the underfitting, and the other is the overfitting problem and the reality. Now, when we say underfitting, it means that either your model is too simple, or it doesn't say here, but or sometimes even your data is so small, or your data is not diverse enough, so it doesn't represent all the relevant class attributes or the parameters, characteristics. So this brings also, you will see in the following slide, the formula, a high bias and low variance. However, and this also brings low accuracy in both training stage and the testing stage, not only in the testing stage, but even in the very first stage, which is the training stage, you get high errors, or in other words, low accuracy, low F-score, precision, blah, blah. And the other thing is overfitting, and this is mostly faced, the underfitting problem is rarely faced in deep learning aspects, because most of the time, if you use benchmark data sets for deep learning, they will be most of the time with a large number of amount of data and with a lot of diversity in it. And again, since you are using a deep learning model, it won't be very simple automatically, but you will eventually face the other problem in most of the cases when you are dealing with deep learning cases, as the model this time is too complex, and this time it fits some of the irrelevant characters of the training data, which means that it just fits it. Or in other words, you could think of it like an analogy, like a memorizing student. He or she only memorizes when studying for an exam, but really doesn't learn. So in the exam, if some different types of questions come, he or she fails. So it is just like that. In overfitting, your model extremely overfits to the training data. This brings a very good accuracy or very low error regarding the training phase, but don't get lured to it, because when you pass to the test stage, there will be great performance degradance in terms of accuracy, F-score, blah, blah errors. So this brings low bias and high variance. So when we come to the overfitting part, so think of these red marks as your data set. And this is the representation of your model. It could be a multi-layer perceptron or deep learning, whatever. So as you see, it tries to fit to all to the most of the data points. So however, a new data comes very different from these points, the distribution. It cannot predict accurately. This is the problem, because it has a very large variance due to extreme adaptation to the training data. And the other one, in the underfitting problem, like this line, like a regression. So as you see, it just cuts and it doesn't fit most of the points. So this brings both in the training and the test low accuracy, both in training and testing. So there is also unavailable error. However, the bias and variance are the ones that we try to minimize them. It is very difficult to both minimize them, but if you succeed in that, then it's a good thing. So as you see, in underfitting, the error is in both training and testing, it is relatively high. And when we think of the overfitting problem, well, the training error is near to zero, very good. But again, there is a big difference between the training performance and the test performance. And this brings the other problem, which you mostly face in deep learning models, because if your model is too complex, you will eventually have this problem, overfitting, as you see the complexity, and with low bias and high variance. So the machine learning is just optimizing the weights if you are thinking of deep learning models, because mostly of them are based on neural networks, and some of those were variations. And as you see, the classical learning algorithms like statistical learning and so on, it doesn't change with the amount of data. This is one of the things that really fascinated me when I first introduced myself to the concept of deep learning years ago, because this is the crucial thing. I mean, the amount of data increases, yes, diversity increases, and eventually, interestingly, performance increases. This is the classical learning, but when we come to deep learning, it is really interesting. So more data, more noisy data, more outliers, it learns better. So this is very interesting in the case of deep learning. So in machine learning, like a classical multi-layer perceptron, which we will discuss shortly, with one or more, very few amount of single or more hidden layers, but a lot of layers. But not only the crucial thing is the number of layers in deep learning, keep in mind, a lot of much more attributes to be updated, a lot of different, much more amount of hyperparameters in deep learning when compared to classical feed-forward neural networks. So this is a nice analogy with the operation goes on like this. So this is your original input, and it starts with the low-level features, and within each stage, thanks to some convolution filters or kernels, finally it becomes like this. As you see, these are not very meaningful for human eye, but very meaningful for the computer vision. So sometimes the classical feed-forward neural networks or multi-layer perceptrons are named as shallow neural networks with one or more hidden layers. And in deep neural network models, there are a lot of hidden layers. But again, I should say that it is not only the number of hidden layers, it's the number of parameters, and the mathematical approach in calculating and updating these connections is much more sophisticated and advanced in deep learning models, most of them, not all of them. So that is the question. And what is really useful, and it is used nearly in everywhere you can guess right now. So I won't say where deep learning is used, blah, blah, blah. It is used in nearly everywhere. So, and the crucial thing is, it's an end-to-end learning system. What do we mean by end-to-end? It doesn't necessarily require, like in a classical data mining or classical machine learning algorithm, first you analyze the data, pre-process some of the features, and you feature reduction, feature selection, principal component analysis, blah, blah, and then use some algorithms or manually change the parameters of some attributes and so on. No, it deals with the data almost by itself. So it is the crucial part in deep learning models. However, you also deal with some other things, and these are much more time consuming in terms of deep learning, which is the hyperparameter tuning. How many hidden layers, how many convolution layers, what optimizer, which learning, adaptive learning methodology you will use, which initial learning rate, and what will be your batch size, and what will be the regularization parameters, L1 loss or L2 loss, or the combination of both. What will be the method for getting rid of or mitigating the overfitting problem using dropout or some other mechanisms or both, and what will be the loss function, and so on. So there are a lot of different things to be considered in deep learning, hyperparameters and architecture of your model. So before we pass to some of the deep learning models like convolution, LSTM, and so on, first of all, just a reminder, or for the ones who don't know, just a short introduction for artificial neural networks, shortly ANN. So they are just inspired by the mammalian brain cells, and the basic idea is that for each node neuron, there are some weights initially randomly initialized and then updated according to some gradient or some other loss algorithm. And the idea is you just get the simple multiplication and the addition operation, and then you use, if you like, a bias, and then you get an output. And this output could be this like simple ramp function, or it could be another nonlinear activation function such as sigmoid or tangent or rectified linear unique, leaky value, etc. So this is the very first model in the history, Rosenblatt, It is a very, very simple model, and it is called only a single perceptron. There is no hidden layer. There are only some inputs and an output, and there is only a very linear, simple collector here, and you define a threshold value for the output of this, and then you try to classify according to these models. So this was not very effective for nonlinear problems. So eventually they derived two things. First, a hidden layer, and like this one, which is called feed-forward neural networks, or in other words, multi-layer perceptrons. One input layer, one node or many nodes for multi-classification, output layer, and any number of nodes for a single hidden layer, or more hidden layers, but the first one with a single hidden layer. And the crucial thing is the activations here and here is not a very simple step function or ramp function like this one. It is a more nonlinear and more interesting function, like a sigmoid function, which derives an output value, whatever the input is. And they also use afterwards some other nonlinear activations like tangent and so on. So what is the idea? Is the crucial thing here is the inputs are represented by each of these nodes, and these weights, and it doesn't show here, if you like, you can use biases and these weights, and you get an output here eventually. So when it goes to the forward pass, for each of your instances records in your data set, and these are the representations, weight, height, gender, etc. And it calculates and you get an output, whether it's a regression problem, a numerical output, or it could be a classification problem. Let's say, since it's a single node, a binary classification, true or false. So your prediction and the original actual data, and it gets an error. Now, the crucial thing is these weights, coefficients, I should say, are initially random. So what is the interesting thing is within the training process, these random weights should be updated in a reasonable manner. What I mean by reasonable manner is using some hinge loss or some other squared loss and gradient and backpropagation. So within the training process, for each of the outputs, if there is an error, this error is propagated and it updates all the weights here and all the weights here. And eventually, for the second record, if it's stochastic learning, each record, for each instance, the weights are updated, or batch learning, after some operations, then the weights are updated. These weights are updated. And when you finally end your training stage, these weights will get their final values. And eventually, by using those weights, most of the training data is now being classified accurately, or it's a numerical prediction regression problem with a very low error. And the methodology in updating those weights are based on just the optimization problem, and it is based on a learning rate, with the coefficient, and some gradient operations. And this is very crucial because think of a ball. If the energy is very small, it doesn't come to the global optimized point. It may be stuck on the local optima, or it could be here another local optima, but it should be getting to the global optimum point. So the learning rate, by using learning rate or momentum and some other methodologies, the idea is getting the minimum error. So your minimum error is eventually also the error in the output for each of the records. Your model tries to learn from the data and tries to minimize this error, and it uses this gradient momentum approach. Like this is the learning rate, and the error is propagated with the gradient descent approach. So if the descent is controlled by the aid of the gradients, then it can get to the global optimum, or very near to the global optimum. And the thing is, another important thing is this partial derivative is according to the weight. Now, think of this problem. In this problem, we have 3 dimensions. So think of this an optimization function. Then you will have f, x, y, z. So x, y, z are your 3 dimensions in this problem. Now, think of our model, and think that for this model, you have 3, 4, 12 weights here. So let's suppose that we didn't use any bias. And we have also 6 weights here. So there are a lot of weights, which means that we don't have 3 dimensions. We have many dimensions. So in other words, this gradient is the crucial thing, because as you see, the weight is updated according, each weight is updated. So the whole system is like a many dimensional model. So this is very crucial, and we get the gradient of the error according to the weights. So that's why we use the derivative, and by the aid of the chain rule, we use the upstage. So there are a lot of things in those we can discuss, I can discuss, but due to the shortage of time, I'm just passing forward. But this is very crucial in deep learning and machine learning. So this means that you should be using nonlinear activation functions, like the logistic function, or like this one, hyperbolic tangent, or softmax, especially for multi-class classification and in natural language processing mostly. And also in most cases, convolutions after the convolution layer is mostly used, and sometimes in LSTMs and some other models it's used. This is also another nonlinear activation function, much simpler. So the derivative is also very faster and simpler. So it is mostly preferred in most of the deep learning models, and some other deep learning mostly used, not all of them. Some of them are given here, and the derivative. So you use the derivative to calculate the gradient error and the backpropagation. So the convolution neural networks, this time, there is an interesting operation within this system. So this is one of the pioneers and current hot usages of deep learning. They are primarily designed for image data, which is a big problem for our classical trends. So even with the classical multilayer perceptron like this, you cannot effectively classify image data. But if you think of also object identification, object description, it is nearly impossible for these models, and it is nearly impossible for k-nearest neighbors or decision trees and so on. So these guys have made a revolution for those types of image-based problems. So the crucial thing is, one of them is the convolution operation, and this is also known from the image processing. In fact, this convolution operation is not invented in 2010s. It was known even in the 20th century for computer vision and image processing books. You could see convolution operation. So this is a very simple example. So you get an input matrix and use a convolution filter, and you use just element-wise multiplication and then addition and get the result. So this is a convol feature. And what is the idea here is, I will just show why it works very effectively in image data. This methodology is, now think of this inner picture of a room, and you use some filters, and one of the filter is this one. So when you apply this filter, I couldn't activate the animation, but it will go on within the whole image of this data. So this is the original image, numerical image, and this is your filter. It will be running through the whole input image, and it will get you a convoluted image. And if you use these filters, for instance, you use different filters, of course, you get different features. So this will be the eventual output within the first convolution. But this doesn't apply to the output of your algorithm. Don't get me mistaken. This will be used in a further round with different filters for different purposes. And in the final round, it will be a very, very different image. But each purpose is to get some of the crucial patterns, aspects of the original image that will be very useful for the computer to correctly classify this image. So sometimes the edge, sometimes some other parts, sometimes some other patterns. So there will be a lot of different filters. So that's the power of the convolution operation. And we are not limited to the convolution operation itself. After each convolution operation, most of the time, an activation, nonlinear activation is again used like in classical multilayer perceptrons, and most of the time rectified linear units. And as I told you, you do not use only one layer, you use many layers. So within each layer, you get a new feature map. And you are not done with convolution plus nonlinear activation. After that, sometimes, not always, you can use either max pooling or average pooling, which also reduces the spatial size, gets a subsample of the convoluted image like this one. For instance, if you use a max pooling, so this, let's say that we have come here, and after that, we get only the max values from each one. So you get this output. And for instance, you use some convolutions and poolings and convolutions. It doesn't show here. After each convolution, you also use an activation, nonlinear activation. And finally, for instance, in our case, we have 5 classes. And this blue part is in most of the convolution neural network architectures, the final rounds, we do not use convolution or pooling. In the final rounds, but not always, in most of the architectures, you can use some fully connected layers. This part looks like a multi-layer perceptron or a fully connected neural network. Sometimes it is called dense parts. So with the neurons and weights again, as I told you, and in the final output, there will be output nodes. For instance, since we have a 5 different classification problem, this means that we will have 5 nodes and a softmax eventually function, and it will classify this image as according to whatever it is. So this is the stage, as I told you previously, and within each convolution, we have this most of the time rectified linear unit or some other activation function. And then if we like, you are not mandatorily using pooling. Sometimes you can use pooling, but in some of the very well-known architectures, sometimes they use convolutions one after the other with no pooling, and some after stages, maybe only once pooling could be used. It depends on your architecture. And of course, there are a lot of different things to decide upon. Should you be using, for instance, 2-to-2 filter for max pooling or 3-to-3? Or how many filters are you going to be using? Or how many convolution layers are you going to be using? And what will be the parameters of your filters? Which filters will you use? Only edge detection or something else? So there are a lot of different things to be choosing from. That's why nowadays, most of the people prefer pre-trained models, which is also called the strategy as the transfer learning. So there are very well known some architectures, convolution, which are used for ImageNet or some other competitions, benchmark data sets, gets very good results. So you use those models, you get those models, only train the final parts for your problem. But the initial weights you use from the original architecture, the convolution layers. And also another important thing is, when we come, for instance, this problem, as you see, there are also some fully connected. Let's say there is also one hidden layer here and then an output layer. Now, if there is an error, as you can recall from the classical neural networks, the connections here will be updated. Okay, but only these are updated. In most of the cases, unfortunately, in tutorials, in presentations, what I've seen, or even in some books, it doesn't explain it, or in internet, in a lot of free resources, it describes it incorrectly, or you can get it incorrectly. The thing is, not only the final connections here are updated, the backpropagation is applied to all of these layers. How? Well, you can guess. The filters are updated. So this means that the crucial thing is you do not always use this filter. So in the backpropagation, these will be your weights. So think of them as weights. Well, mathematically, they are weights also. So let me show you. Yes. Now, as you see here, the kernel values, these values are in fact your weights, which I have described in the classical multi-layer perceptron. These guys, so these guys in the convolution part becomes those your filter values. So they are also updated. So in order to update them, that's why we use after each convolution, there is a nonlinear activation function. It should be. So, And what will be how many iterations? It depends on your design of your architecture. So this is one of the common models. Like you get the inputs, and if it's color photos, images, you should get 3 channels. So red, green, blue mostly, and convolutions and sometimes pooling, as you see, and the final fully connected layers, and finally you just predict the paths. So this is the operation, as each corresponding value are multiplied and then added, which is simply the convolution, and you use multiple convolutions. And this is one of the very well-known architectures. However, unfortunately, even today, it is being recalled as an old architecture. So for transfer learning, or in other words, pre-trained learning, now it is not used nowadays, but it was also used as a pre-trained model 5 or 6 years ago. And approximately 10 years ago, this was the winner of the ImageNet. And let me also recall the ones who doesn't know ImageNet competition. It's a very hard data set. I mean, it was a very hard data set regarding more than millions of different images, but keep in mind with 1,000 different classes. So the classes are the photos, and very small photos, RGB color photos of very small pixels, approximately this size of pixels, of different types of ships or cars or cat or tiger, apple, and so on. So 1,000 different categories. And this is a benchmark data set, one of the very well-known benchmark data sets. There are some other different benchmark data sets you could see on the internet, but this is one of the very well-known ImageNet. And this was the AlexNet architecture, who was designed and used by Alex and his friends, colleagues. And as you see, what they did originally in the first round, they used, interestingly, a bigger convolution filter only for the first round of the convolution with a big stride. Now, usually the convolution filter sizes are 3 to 3 or 4 to 5 or 4 to 5 with a stride of 1 or 2. But since they use the bigger convolution filter size, they use the bigger strides. And then for following rounds, they used more conventional convolutions like 5 to 5, 3 to 3. And after these convolutions, they used max pooling and another max pooling here. And they used 2 fully connected layers, which we call as dense layers. This is like the multi-layer perceptron architecture. So we are done with convolution and pooling action. And in the final round, we have a softmax function with 1,000 output nodes for 1,000 classifiers. So it also gets the top 5 classifications. So, of course, it works very fast when it comes to testing, not only training. So it detects it like this one. And there's also another mechanism you should not forget is flattening. Because why? Well, let me tell you, in most of the graphics or figures, I should say figures, when we further move on within the convolution and pooling operations, it is represented or depicted with a 3-dimensional shapes, because in fact it is like that, because starting from here, since we are using different number of features, mathematically it becomes a 3-dimensional matrix. So the whole data should be operated in the final rounds like a neural network. So in order to be used as a conventional neural network, what you should be doing is you should be transforming that 3-dimensional matrices into a 1-dimensional vectors, which we call the flattening operation. And then we could just operate this part, and we could then finally get the result. So this is like the flattening operation. So in the final round, even if it's a simple, very simple data like this one, this will become eventually 8 to 1. So 8 input nodes, and whatever you design for here, it is up to you, the hidden layers and so on. Another architecture, this is still in use. However, keep in mind, this guy requires a lot of memory if you are going to be retraining it from the scratch, only using the same architecture. But if you are going to be retraining this whole architecture on your computer, still today, it requires a lot of memory and computational power also. This is a VGG net. It is more advanced than AlexNet. and its accuracy is better than AlexNet, these two guys, for ImageNet problem, for classification. They were also used for other problems, but we will come to that because currently new technologies are used for object detection or identification and so on. But this was used especially again for multi-class classification. As you can see the architecture, and this is the number of convolution filters, how many filters are used, and pooling mechanisms, and finally fully connected rounds. Another interesting architecture was Google Net or Google Net, which brought the inception model. Inception is an interesting story, and it is used in a lot of rounds here. As you can see that it is a combination of, at the same time, using more different at the same time, and some of them are very interestingly pixel-based convolutions, one-to-one convolutions. So they are used only to change the parameters of that pattern itself. But some of them are basic convolutions, conventional convolutions, like 3-to-3 or 5-to-5, and then they are all concatenated finally. So this is an interesting architecture, inception model, and it is a total of 22 layers. And in some of the layers, these inception models are within this architecture. So it was also another winner, which also surpassed this VGG nets, and it was the best one at that time. And another architecture after that, these models brought some other problems like vanishing gradients. The weight updates become much small and small, so there were some other problems, and also the computation inefficiency. So another approach was rest nets, residual nets. So this is also one of the transfer learning pre-trained architectures still in use. So it is very interesting in residual net. Then we are introduced the connection skipping. So as you can see, this is a classical 34 layers convolution neural network, but this is another 34 layer, but an inception approach. So residual approach. So what we mean by residual approach is, as you can see here, so they are finally, this output is added piecewise addition to the vector here, and then it goes on. So why was this used? To get rid of the vanishing gradients, and it was also effective due to the accuracy performance. It also improved very slightly the accuracy performance and so on. So it was a really interesting approach. So it is still in use today as pre-trained models, this residual approach. So as you see, ResNet, and of course, these are the percentage of errors. If you subtract it, and you can, for instance, this is approximately 96% of accuracy, you could say, for 1,000 different classes. However, keep in mind that, don't get me mistaken, these are top 5 scores, not top 1 classical accuracy, top 5 accuracy, and so on. So this Google Net was a bit more advanced layers. There are also some other convolution models still in use today, and you can also use these as pre-trained models, like network in network, fractal nets, squeeze nets, mobile nets, dense nets, and so on. So you can use this. And before we go on, let me also say something. I forgot to include in the slides, but I could say it here. What do we mean, or what is meant by pre-trained models or transfer learning? Now, these models has already been trained, and the accuracy has already been calculated for training and tests. For instance, if you get, let's say, this model, so VGG19. So what do you mean by transfer learning or using as a pre-trained model? You can have different strategies. Now, this model has been trained for 1,000 different classes. And let's suppose that you have 26 different classes to identify 26 different car models, okay? Automobile models, so pictures of automobiles. So what you should be doing is, of course, if you directly change this softmax output layer to 1000 to 26 and then input the images, you get nothing, you get error. So you should be retraining some of the data as your training data. So what should be retrained again? Some of the weights should be eventually updated. So there are different strategies in transfer learning, or in other words, pre-trained models. First strategy is just train the connection between the softmax and this fully connected layer only training for the output classification layer. Well, most of the time, maybe it won't be necessarily enough. Then another strategy is just train the fully connected layer. So the strategy is called freezing. So the other parts are used as the original final weights within this model. You can download the weights. So you use these weights as originally, which is freezing option, and you defreeze these parts and you retrain these parts. This is the second strategy. You only retrain this part is the first strategy. Second alternative, if it's not enough, then defreeze these parts, freeze these parts again. So these weights won't change, only the weights will be updated here. If it's not enough, then you could also, as a final chance, just defreeze these parts. So this means that it will be taking a lot of training time this time, because you should be retraining these weights also. So this means that what you are using is only the architecture of this guy and only the hyperparameters, ADAMAX, ADAGRAD, whatever they have used as the learning optimization, and what was the initial rate, the same initial rate and the same convolution filters and the same initial parameters with the initial batch sizes. But retraining the whole your network is another transfer learning architecture strategy. Okay, but we are not done with convolutions yet, because they are very, very important today in artificial intelligence areas, because they are not only used for classification, they are used for these types of things, for other computer vision tasks. Only semantic segmentation, and by the aid of this, using more advanced problems like instance segmentation, object detection, or classification and localization for single objects, and even for multiple objects. Now, today's our computers, thanks to some of the new convolution models like regional models or YOLO or single shot detectors, we could use these hard problems. One of them is semantic segmentation. If you are going to be, your problem is if this is enough for you, so getting a semantic segmentation of your images, then you could use the downsampling is the classical convolution. The interesting part is an inverse convolution is added to your architecture, and this part, just the inverse operations of pooling, reverse pooling, you could say, and the inverse operation of the convolutions, deconvolutions are used. Eventually, you get the original size, but not the original picture. It becomes like this thanks to this architecture. So this is for semantic segmentation. However, if you are going to be using it for detecting a single object, so you are not curious with the background or many things, you only want to find a cat in any picture, so single cat, single identification, single object. So classification plus it becomes a localization problem. This time, a very different strategy, not this time. This time you can use a convolution like AlexNet or VGG or MobileNet, SqueezeNet, but you add another mechanism. There are this time not only a single error coming from the softmax loss regarding the classification error, but then there is also a coordination error. In other words, localization error. So what you get is you define the coordinates as your supervised learning. For each image, you define the correct coordinates with the XY point, mostly leftmost, uppermost part is here. And if you define the width and the height, then you get a frame picture. So for each training image, you also define the correct coordinates, and your algorithm also tries to guess these coordinates, which you get eventually mostly L2 loss, which is the square error loss is used. So this is a regression problem you can guess. So there will be 4 nodes also, but these 4 nodes, output nodes, are different from the 1000 nodes here. This is for the classification mission, this is for the regression mission, and you try your model tries to correctly guess each of these nodes which represent one of the parameters of the box. So it's a regression problem, but they are all combined here as a total loss, and then it is back propagated. However, for difficult images or more than one image, multi-object detection, you should be getting means of more advanced models. And one of them is regional RCNN. Do not mix it with recurrent. This is not recurrent. This is regional RCNN. This time, there are some regions of interest, region of interest pooling methodology, and also you define some initial frames. So these frame boxes are defined like 2,000 different boxes, and for each image, they are separately executed within the same convolution, but getting different results and then combining them. However, it takes a lot of time. So in order to get rid of that, they are combined with a regional pooling architecture, which is called fast RCNN. And again, it requires time faster than this, but not enough fast regarding the training phase. Make it more faster rather than using the initially defined static regions. Let the neural network decide upon the regions themselves. So region proposal networks with the region of interest pooling, which we have the faster RCNN, is another model that is commonly used. And another very different approach is again for multi-object detection. One of them is YOLO, and the other one is single shot detector. YOLO is the short abbreviation for you only look once. And the idea is, rather than using these bounding boxes, you just divide the original image into previously defined grids, and you execute different grid combinations to define the parts for each different object, and then they are both combined, this error and this error are combined to train and get the final detections for each of these objects. So this is YOLO, and a similar one to this is single shot detector like this one. And today also, what they are also using to make it much more efficient, what they do is, for this convolution part, you do not train your data from the scratch, and you do not design a convolution. What you do is you use a previously trained base, which is the pre-trained model as a transfer learning strategy, and you combine it for adding these mechanisms in your code to make it much more faster. Now, when we come to the recurrent neural networks, this is the RNN. So this is for the sequential data. It could be used for time series and mostly text, natural language processing. So the idea is the data is brought back from the previous round, which is like this one. As you can see, in the previous sequence, the data is processed for the next sequence. These are the pioneers of the original systems. And this is one of them is the simple recurrent neural network, which is this is a Jordan. So think of it as a classical neural network here. The difference comes from the pioneer single recurrent is the output node. The copy of it is also fed to the state layer. Each output node corresponds to a state node here. And in the next round, the previous round output is also calculated, multiplied with weights, and added to the hidden layer round. So this was a very simple recurrent model, Jordan. Another model, Almond. Almond, the only difference is the hidden layer, the node from each hidden layer is fed again to the context or state layer. So this is the notation of that. So T-1, as you can recall, the output coming from the previous round. In one of them, as I said, in the Jordan model, the outputs are fed from the previous round. And in the Almond model, the outputs from the hidden layer, from the output layer, from the hidden layer. So this is notation, and most of the time, these are, as you can guess, for those networks, logistic sigmoid or tangent were used. But we will see now in today's deep recurrent neural networks and in LSTMs, some other mechanisms and other activation functions are used. So, how are we going so far? would you like me to give you a short 5 minutes break, or do you have any questions, or shall we continue?
It depends on you, Mete Hocam.
Okay, so if everyone's okay, I'm continuing. I'm going on. Okay, thank you, sir. So when we say the recurrent neural networks, they are basically the idea of this operation, but you are not limited only to the hidden layer or to the output layer. You can use any layers which gets the previous data and then uses it for the next prediction. And keep in mind that the crucial thing is the recurrent neural networks are effective if the data is a sequential pattern like natural languages, since each word follows another word in any human language, or some time series problems, whatever you use for trend, sales, forecastings, and so on. And so they are also, in addition, used adding the convolution or object detection models, like I told you before, like YOLO. If you include them and combine them with the recurrent neural networks, you can also get very, very interesting results, satisfactory results for some sophisticated problems like image captioning. And there is also another interesting case is the bidirectional recurrent neural network. So within each round, not only the data is processed in one direction, they are processed in both directions, forward and backward. So what I mean is both directions is, since let's suppose that you have a time series data, 5 different or 100 different calculated values. So you start from the first one in the forward, and then in the backward you start from the 100 one, and they are both executed, and finally there is a concatenation function that gets both these and combines these as the final output, which is the bidirectional recurrent neural networks. They are sometimes very effective for some of the very advanced signal processing problems, voice detection, musical instrument sound detection, or some of the natural language processing problems. These guys are used. So when we come to the deep recurrent models, one of the most popular one is LSTM. And interestingly enough, maybe most of you know, but let me say something interesting. This model was proposed by a German scientist or some colleagues in 1998, but no one regarded that article at that time because the computers weren't effective enough even for a single LSTM to be properly working. So that scientists article had gathered the attention in 2000s or the beginning of 2010s, thanks to the advance in computer computations and so on. So you will see why, because for a single LSTM is also, it can be thought as a advanced model or deep model, because there are different copies of the same data. So if you have, for instance, 1000 input nodes and 100 output nodes, the same will be used within each of these gates, and also a copy of those. For instance, if you use the 1000, let's say, output nodes, a copy of each output will be used as the T-1. So another 1000 for each of these gates will be as state or context. And since, as you can guess, there are 5 different gates and 5 different activation functions like these. Some of them are tangent, some of them are sigmoid. So even a single LSTM is an advanced model. And LSTM can learn, because it's the shortage abbreviation for long short-term memory, LSTM can learn long-term correlations with the data sequences. If you want to learn not so much longer, but less longer, you can use a gated recurrent unit. I will come to that. Now, that's what I'm saying, okay? So this is one of each of the activations. And even if you use a very simple architecture like the input nodes, one hidden layer and output nodes, keep in mind that for each hidden or for each output node, there will be also a copy of those. So as you can see, for each of these output nodes, for instance, there will be the copies of those for context layers. So each of the prediction will be fed for the next round as the T-1 data. So at T0 for the first information, the feedbacks will not be activated. They will be 0. However, starting from the second record, they will be also fed back. So there will be a lot of extra connections which make this LSTM interesting enough or complex enough. And these are the element-wise multiplication within the vectors. So which each element, so since there are 1000 nodes, let's say, for each of these, so there will be 1000 vector here, 1000 to 1 and 1000 to 1, piecewise multiplications and piecewise additions. And this is also another activation function. And in some of the activation functions, we use tangent. These two are tangent activations, and these three are the sigmoid activations for the activations. In some other architectures, they can use rectified linear unit to make it faster, and so on. And if we compare it with a simple recurrent model like this one, which I discussed, the pioneers like these guys, this is the difference which makes it much more advanced. This is a simple recurrent cell, and this is an LSTM cell. So as I told you, and again, in this case, there is only, let's say, if we are going to be getting the inputs from the output nodes, there will be an extra, let's say 100 nodes, suppose 100 output. However, there will be extra 100 nodes for that cell. So due to the computational complexity, and in some applications also, due to the overfitting or some other problems, less advanced model, GRU, is also preferred today in some systems. This is a simpler version of LSTM. We have less gates, and the forget and input are put into an update gate. And the cell state and the hidden state, these two states are also merged into one. So especially if you need long-term correlations, but not so much long-term, I mean, for instance, for the sales forecasting, if you need to remember the previous 4 sales, but not previous 100 sales, then rather than LSTM, you could give a chance to this guy, GRU. Now, these models are effectively used in natural language processing for mostly the machine translation, because before the approach by the aid of LSTMs and deep learning approach, the models that were used weren't effective even for English to French, French to English translation. Recall, for instance, the Google Translate 10 years ago or 12 years ago. It was based on, unfortunately, statistical Bayesian language modeling, and it was very, very ineffective. I'm not even thinking about English to Turkish, even English to French or vice versa. It was very ineffective. Now, this guy brought a new era by the aid of the deep learning and LSTMs. So since each word in a natural language is a sequence and it's a sequential pattern, so if we train it with previous selected sentence, correct sentences for English, let's say, and their counterpart French, so and if we train with those, then a new data comes. It will be using an encoder and decoder model like this, which is also based in Google Translate. I will show you. And by the aid of LSTMs, it could learn. But even this was not effective. Keep in mind, we will come to that. This is not the popular, what you call is GPT, chat GPT, blah, blah, blah. It is a different story. We will come to that. But the pioneer was using LSTMs. However, in today's large language models, they are, again, encoders and decoders are used, or one of them are used, but they are not working like this because they are not using LSTMs. They are not treating the human language like a sequential pattern. They are treating them all in one. Yes, the current ones, like, you know, GPT, blah, blah, they are using, again, deep neural networks, but an interesting attention mechanism instead of these LSTMs. So again, it could also be used not only for neural machine translation, it could also be useful for, the LSTM sequence-to-sequence models for chatbots. For instance, in English or Turkish, you write something, then the computer outputs something else. So again, using two encoder and decoders, one encoder, one decoder. However, keep in mind that in order to work this model or translation models, you should be first training with a large amount of correct data. Okay, so training process is a really hard, arduous task for natural language processing today. And this is the Google Translate. I'm not sure the current Google Translate is still this one, but I can assure you that 5 years ago, this was the new Google Translate, which was far better than the previous one, the Bayesian language modeling. It is much better than Bayesian language modeling, and it is based on 8 layers of LSTMs. And you can recall in the first layer of the encoder part, it is a bidirectional LSTM. They could have used bidirectional in the foregoing layers also, but they preferred, in terms of the computation complexity, to make it simpler, they used only in the first layer, and it was enough. So in the first layer, the sentences are processed forward and backward and then combined, which is bidirectional LSTM. And then the other layers. So keep in mind that they are not using a single LSTM. They are using 8 layers of LSTMs. And they are using an attention mechanism, but this attention mechanism is a bit different than the one that is currently used in today's GPTs, ChatGPT, Google Palm, Pathways, etc. But again, an attention mechanism, I will explain it later on. And then in the decoder part, again, this time only single-sided classical LSTMs for the decoder part. So encoder and decoder, which is the basic architecture of the Google Translate. And there's also another approach, including convolution plus recurrent neural networks, convolution plus LSTMs, which is a difficult thing, image caption generation. So it could also be used for question answering. So you can effectively use, if you use a convolution plus LSTM, what is in the woman's face, or what is that mustache? It could answer correctly as a banana, or it could get a caption, a summary of this picture by the aid of both convolution plus LSTM, like these ones. So today, they are not a difficult task, even they were generated 8 years ago. So they are much more accurately working right now. The AlphaGo is also another interesting approach. It beat the Korean world champion in Go games. And the idea was not only a convolution neural network, but it was also connected as an output to a reinforcement learning as a policy network. And it also used a Monte Carlo method to choose upon some strategies. However, the most effective, interesting part, which is a revolution in games, is the inputs are just some different moves within some games. So the images are fed like the screenshots of each game moves were input as images. And thanks to also not only the convolution, but using reinforcement learning policy and Monte Carlo, it beat the human beings. So again, another difficult task is visual question answering. Again, using convolution neural networks plus recurrent neural network, mostly LSTM, convolution plus LSTM. So it answers effectively a given image as the answer to the question. So this is the current topic is the transformers, which uses a self-attention mechanism. And one of them is the very famous attention is all you need article. So this part is the encoder and this part is the decoder. However, keep in mind that the first proposed model and nearly all of the models that are in use today, like the Google Palm and the BART, Distal BERTs, GPTs, even today, they are based on this very basic model and this mechanism. The difference is how many layers you use, and some of them use only the encoder. some of them use the decoder, and some of them use both. For instance, interestingly enough, all of the GPTs, including ChatGPT, uses the decoder. And the difference between these GPTs and ChatGPT, I will just explain in the further slides, is based on a reinforcement learning in the final process. But the interesting thing is there is no convolution, and there is no, of course, no convolution, but there is no LSTM. There is no recurrent model. There is no sequence. The interesting thing is a revolution is that for a lot of different natural language processing problems, including machine translation, text summarization, question answering, keyword subtraction, etc., whatever you use, you can use only this part or both, but these are some basic fully connected neural networks. However, the crucial mechanism is the self-attention and an extension of it, which is named as the multi-head attention or masked attention. And sometimes these models are named as LLMs, which are large language models. So some of them are like BERT, bidirectional encoding representative as encoder only. This architecture is used. Of course, the number of layers are different. Some of them use both of them, encoder, decoder, T5. Most of the people do not recall that, but this is also a very strong architecture, and BART. And there is also the decoder-only models, GPTs, XLNets, and ChatGPT, etc. So as you see, the idea is using a self-attention mechanism and a lot of whatever you use, how many layers you use of these classical feed-forward neural networks, and in the decoder part against an attention mechanism and feed-forward and softmax. So what is this attention? Now, the nice part is this one. The self-attention mechanism is very simply, think of any language. This is given in English, but it could be Turkish, whatever you use. So in this sentence also, when we recall this he pronoun, this relates to Jack. So how do we get it? Because thanks to our brains, our natural language learning capacity, when we see this sentence, we automatically get that this he is related to Jack. So this mechanism is somehow effectively applied to the computers in attention mechanism in these transformer models. So it also learns that this he is this he, because this is important. Who is tired as a question answering from this data, or if you want to translate this to Turkish for correct translation, or to German or French, which also has pronouns like in English. So this is the mechanism. I won't go into the detail, but the idea is just focusing on that. Or another self-attention example is when we think of a sentence like this one in Turkish, karşıya doğru yüzdük. When we say that yüzmek is has many meanings in Turkish, we automatically do not get use as the number 100 or our face. We directly recall it as swimming, because we are automatically getting attention to the karşı term. So that's also a human attention mechanism, which is very interestingly and effectively applied in these large language models, in these transformers. And another crucial thing in these transformers is the transformers use a semi-supervised, not fully supervised, which means that first unsupervised pre-training over a very large data set, and then supervised fine-tuning for whatever you need. So if you are going to be using it for question answering, another different supervised fine-tuning, or sentence generation, another supervised fine-tuning, chatbot, another supervised, machine translation, another supervised, and so on. So this is the crucial part. And they can be used, as you can see here, for different parts. The supervised fine-tuning is done. So this is the basic difference between the GPTs. All of them are using this part, the decoder-only model, and using these attention mechanisms. And the difference is the number of layers and the size of the tokens. And when I say these tokens, as you can guess, of course, there is also another important advance in these type of problems is just converting each word to a vector, which we shortly say word to vec. So when you vectorize the words in that natural language, English, Turkish, blah, blah, you define a static size of arrays, vectors for each term, and they are trained, and they represent very meaningful scores or values, and you use these tokens, which are each of them represent one of the unique word in that language, human language. So they are used numerically, and in GPT-3 it is much more higher level. I'm not sure what is the number of layers in GPT-4, which is last month has been announced, but it should be more than this, because the total number of hyperparameters in GPT-4 is said to be 100 trillion, not even million or billion. This guy, GPT-3, is somewhat, I don't remember right now, is a billion, some 100 billions, but in GPT-4 it is trillions, so it is also crucial. And this is the different usages. So it could be used for common sense, it could be used for world knowledge, it could be used for logical reasoning, and so on. So, but the thing is, not only with the GPTs, but in all of these transformer models, you should be training the unsupervised part with a gigantic amount of data for that language. Okay, so you can see here, and it requires, of course, a lot of memory and a lot of CPU, not only CPU, but GPU power. So it is really a complex architectures. And there's also other models. There are a lot of alternatives, but I would like to mention this guy also, BERT bidirectional encoder. This is different than GPTs. GPT means generative pre-trained, so you know pre-trained, and generation, you know it. So this uses decoder-only model. So GPT uses decoder-only, and BERT is a bidirectional encoder-only. It only uses this architecture, this part. And these are some competitors with ChatGPT and GPTs. Google's pathways language modeling. This is also interesting. So again, we have multi-self-attentions and classical neural networks feed forward. As you can see, there is no recurrent neural network, no LSTM, no convolution, blah, blah. They are fully connected models, but with the power of the self-attention mechanisms and the power of advanced architectures, like in this one, in Google Pathway Language Model, PaLM shortly, it has this amount of layers cascaded together with 540 billion parameters. So let's come to the very, very famous ChatGPT. Now, ChatGPT is interesting. What is more interesting is chat boxes and chat mechanism are within all of these. And chat mechanism can be used for this also, if you train it correctly. And chat is used in all of these guys also. There were a lot of chat engines, chat boxes in these also. So why everyone is hyped all around the world, billions of people are hyped with the ChatGPT. The interesting thing is adding a reinforcement learning. So when we think of all of the models that we covered so far are either supervised learning, classification, or unsupervised, blah, blah. But ChatGPT, interestingly enough, adds a final mechanism after the classification part, a reinforcement learning. And this reinforcement learning is, interestingly enough, first, some humans, yes, humans are assigned to get some different chat responses and scores them and ranks them. And then they are backward trained, and using the reinforcement learning model, it rewards or punishes the alternative responses. So it much interestingly learns and adding the reinforcement learning mechanism, first human feedback and then reinforcement learning, ChatGPT is different. So that is the interesting idea in ChatGPT, what makes it maybe much more hyped or popular. So another world in deep learning is the autoencoders. So this is interesting. This is an unsupervised learning model. So there are different models of these, but shortly to say, what do we do is, it is a very interesting system. So in the encoder part, this could be either convolutional, but it could also be classical feed-forward neural network, less hidden layer, less node hidden layer, and just the opposite number of hidden nodes in these layers. And one of the very popular usage of autoencoder is getting a new version of this image. You could say, hey, this is not clear as this one. Yes, but for you, not for computer vision. So one of the very useful part in autoencoders is just inputting your images and getting additional versions of your images, which could be useful for your convolution neural network for object classification or object identification. And it could also be added to your training data set as a mechanism for data augmentation to make your data more rich, more diverse with the original images. For instance, if you don't have a lot of different teacup images like this one, you could also get different versions of these by the autoencoders. And some autoencoders, some advanced autoencoders, like variational autoencoders, could also be used to enhance the images or to correct the images. So this is a simple version of it. It could be a classical neural network. And the cost function is very, very simple. Your input, each pixel is your value, and this output image pixel value. So this is the cost function, which could be used for the backpropagation. And also sometimes you could use autoencoders like image segmentation, the same architecture, but not for image segmentation, but getting this part and correcting this part, like convolutions and up convolutions, UConv up convolutions, like in this one. As I told you in the previous session today, there was a similar architecture, but its aim was different. It was used for image segmentation. This time, as an autoencoder to correct the image, these models could be used. So, and this is again the loss function. However, now we are coming to another popular part, which is attracts most of the people's attention, is GANs, generator adversarial networks. But to make it short and to go faster, I will say GANs. Now, generator adversarial networks, interestingly enough, there are two neural networks, and let's say by a popular common approach, they talk to each other. They communicate with each other in some way. So, and each one has a role. One of the neural network is a generator, and the other one is a discriminator. So it could be a simple feed-forward neural network, both of them, or they could be convolution neural networks or something else. But the interesting thing is, within the training steps, the generator generates new fake images, new examples of an image, and the discriminator says, hey, this is very, very different from the original. I didn't like it. Or, well, it is similar, or it is exact similar, but in fact, it is not similar. So it is a zero-sum game. So finally, like in this one, it generates this, says no, again says no, but very slightly no. But finally, this is not the original Mona Lisa, by the way. There are some different versions, but this is a new version. But the discriminator says, I can't say anything, or the error is beyond my accepted value. So then the generator gets a new value. So the idea is the generator generates also an error, and the discriminator, so it's a 1-0 game. So they are in competitive, working together or challenging each other. And this is the error generated. So in the generator, the error, 1 minus error, gets the discriminator error. So you total sum up these errors. And so minimizing this total error, which is your loss, and the GAN mechanism, the whole your system is the minimizing this loss, but not making it zero, because if we make it zero, then we get the original picture itself. It is not our aim. Our objective is to generate something similar to the original ones, but a new one. Like this person does not exist. You know, we will come to that slide, but to say it right now, so it generates new human faces, but they are not existing, but they look like an exactly real human face. So that means that this loss becomes minimized, but there is a competition between the generator part generating new images. At first, it is a very big error. So this error should be minimized by the aid of this discriminator. So it gets to a threshold value, then you are finalized. So it is this time. So this loss is minimized to a stopping point, and then you get new images. And there are different models of these, which we will see those. And how do we calculate this loss? There are different versions. One of them is the similar loss to this guy, but this is not effective for GANs. In GANs, we use some other errors for the backpropagation, like Kullback-Leibler divergence or Jensen-Shannon divergence or some others. But again, what I should say shortly is the distributions. You get the distributions and you get the divergence value, difference value, and this could be used as your loss value, and then you can use it as a backpropagation between your generator and discriminator. And you can recall that one of them could be your original input image, each pixel values, and the other one is the output image, the generated new image pixel values. So there are very interesting models that are in use today in industry, in artificial intelligence. So I will just shortly introduce some of them. One of them is the cycle GAN. Now this time, we don't have a single generator and discriminator. Now we have two generators, two discriminators. Oh gosh, let's see. Well, one of the generator, for instance, and the idea is, the purpose is to transform images into new forms and to transform, to get new apples that look like oranges, and also at the same time to get new oranges that look like apples. So in one of the domain, the generator tries to generate fake, not apples, fake oranges, and there is real oranges, and there becomes an adversarial loss here. At the same time, or not at the same time, in a pipeline, the oranges are also tries to be generated as a new form of apple. So in the initial rounds, there will be a great loss both here and here. And then these will be corrected with the discriminator here and the discriminator here. This discriminator will look at the real apple samples and look at this apple sample and say, hey, no. And it will go on forward consistency and backward consistency. So this system, this part and this part are not independent. It is like a cycle. It starts from here, goes here, and then here, again here. So after some iterations, some epochs, finally, you get new images of apples that look like orange, and you get new images of orange that look like apples, which was in the initial study. This is the explanation of it. Was used for very famous horse to zebra. Now, recall that, don't mix it with the pixel to pixel transfer. This was the first one. For instance, you know, the Van Gogh's Scary Night picture was applied to cats' human faces. That was the first one. It wasn't a gun. It wasn't a cycle gun. It was a pixel to pixel transfer. However, there is a difficulty in this one. What is it that you should be supervising? You should be collecting the pairs and saying, hey, I want to pair this one with this one, or I want to pair this sketch with this sketch, which is image to image, pixel to pixel transfer. However, in cycle GAN, you don't have to pair those. You get a collection of what you only do is, it is really nearly a full unsupervised approach, because what you get a collection of different horses and a collection of zebras, but you don't pair this horse to this zebra and transfer. You don't have to say that. It learns it by itself. So that is the power of the cycle GAN. So these are unpaired. So just a collection of horses, collection of zebras, but as you can guess, it is very difficult. I mean, this part, these edges could be transformed into this horse. So there's a very bad picture with some lines here just out of the border of this image and so on. However, when you call this cycle GAN, which is also named as cycle consistent blah blah, automatically you generate new horses and new zebras, as I told you. And this is pixel to pixel transfers, and this is the cycle GAN result for an input like this one. And this is the cycle GAN result. This is what I'm calling. If you don't pair the images, you get some silly results like these, I should say. But thanks to cycle GAN, you can even get a new horse-zebra combination. And it is also used both for Grand Theft Auto and some other computer games, from game to the real street view, or from real street view, game scenes could be generated. It is also very effectively used, another type of cycle GAN, for image dehazing, image corrections. And what is more, not only single cycle GAN, you could use cross domains. So in cycle GAN, we have 2 domains. What about more than 2 domains? There you are, star GAN, 3 domains, 5 domains. So for instance, you could just look at the differences. In cycle GAN, it is not really good in most of the cases, but with star GAN, well, these are the new versions. And also some other advanced GAN models. I have also seen another one of it with using stable diffusion plus GAN for not only pictures, but a whole computer movie, I mean video animation. So a person is dancing, and there is also the animation of it as an animated clip. The current ones is like those, but the pioneers is this one for static pictures. So you get your picture and put it, and the GAN makes it converted into this animated anime art. And image colorizations and super resolution, well, one of the very important words, again with GANs. And there is also another type of GAN, which, you know, this is the most famous, this person does not exist, based on a different type of style GAN. And there is also the convolutional GANs, using again convolutions, but very deep architectures. And these are used to design new interior home designs for architects, interior architects, and so on. And even with using random masks, it reconstructs the image very, very effectively, like in these examples. These are also done with deep convolution GANs, and there we are. Or also, if you like, you can get rid of some of the things, like in these ones. And also facing aging, this is another type of GAN condition. And this was the pioneer. This is not GAN, what I was mentioning before. This is image-to-image translation by pixels, but this is needs a very hard word. The hard word is what you want to transfer. You should be making a supervised learning and also pairing the input image samples. Keep in mind that in all of the GAN models, you don't have to pair the images. So that's the power of the GAN. And also one of the hot topics, text to image by conditional GAN, but don't forget, this is not only by conditional GAN, don't get me wrong. This time, we are not using conditional GAN. We are also using, again, a means of LSTM or recurrent model to get or transformer to get the text data, to process it, and then use it as parameters for this guy, and then use it to generate the new images. And there are also a lot of different applications of GANs, video prediction, 3D object generation. Maybe you have heard a new movie, Last Stand, you could find on the YouTube. It's very new, recent. The script was generated by some GPT or something like that. And the other part was generated by the use of some advanced GANs. Deepfake, you know, again, thanks to GANs, deepfakes are done like that. Melody generation from lyrics, computer game design, designing the game from the scratch by the aid of these GANs. And also I have read an interesting article last week, again, a very recent one. I forgot to add here, PassGAN. If you are interested in information security, it generated passwords, but much more effective than a classical dictionary attack. Of course, it is not a brute force, but think of some passwords like much relatively secure passwords, like using a constant name like November and adding a number, November 1, 2, and adding a asterisk. It also guessed some of those passwords correctly and very fastly by the aid of generator adversarial network. You could find on the internet the article PASCAN, so password generator. And of course, unfortunately, it's maybe it's a good news for some of the cyber criminals. I don't know. And there are also some other models. Deep Q learning. Q learning is a reinforcement learning algorithm, and deep Q learning is using deep neural networks, a lot of feed-forward neural networks, plus in the final layer using a Q learning, a kind of reinforcement learning for games, so for AI-based games or optimization problems. There are some Bayesian network-based deep belief networks. There are some also deep recursive neural networks for grammar construction in natural language, some different theoretical natural language or some other special aspects, graph neural networks, and deep stacking networks. Well, due to the time shortage, and also I can clearly admit that I'm not very popular with those models. I have only some very short amount of knowledge in those models, so I decided only to mention them. There are, but these are also some interesting, very different architectures than convolutions or LSTMs. These are entirely different architectures, so that's why I wanted to also mention those. And well, I think that will be enough for today. Thank you for your attendance. I tried to be as quick as possible, but it took a lot of time, unfortunately. But I really wanted to share at least the parts that I was a bit acquainted or experienced with. So if you have any questions, please do ask. Thank you very much.
Mete Hocam, thank you very much. It was very actually nice overview, at least for me. I have a question related to the generalization ability of deep learning models. You talk about the bias and also variance dilemma. What do you think about bias error and also variance error of deep learning models compared to the shallow models? Is there any theoretical? Actually, there are some theoretical attempts, some results, but what I am asking your opinion, why they work better than shallow models?
Sir, this is a very, very good question. First of all, thank you very much. A really nice question. Well, I think I think it's based on the feature. I mean, what I mean by feature is whether it's natural language processing like the transformers or LSTMs or convolution neural networks. If you use a classical approach, it should not only be a shallow network or neural network, it could also be some other machine learning or data mining algorithm. The thing is, I think the errors, the problem comes from the features. And the success of deep learning is, I think, or the much more relatively less errors, more accurate results, is that the use of or generation of extraction of the features. Because in all classical models, including shallow neural networks also, you design or you generate or you get rid of some of the features, and maybe that's the very first, I mean, I don't know the English term. Gömleğin ilk düğmesini hatalı yükleyince gerisi de hatalı gidiyor. Bence öz nitelikleri klasik yöntemlerle yapmaya çalışmak ya da tüm öz nitelikleri bir resimdeki gibi piksellerin hepsini doğrudan bir klasik neural network'e veya bir karar ağacına yüklemek zaten düğmeyi en baştan yanlış iliklemek gibi gittiği için, yani öz niteliklerin yapılandırılması ve seçimine dolayı gerisi geliyor gibime geliyor. But maybe I'm wrong. But that's my comment.
Okay, thank you very much. It was very nice comment. Thank you.
Thank you very much, sir. Any other questions?
Hocam sanırım soru yok hocam.
Okay. Well, again, thank you very much for all your cooperation and attendance. I took a lot of time, but as I told you, I would like to share all the important aspects, at least the ones I accounted with. So thank you very much again.
We thank you, Mete Hocam.